Okay, let's continue the discussion of a 3 by 3 determinant. Uh, we continue that. Remember, in the last video, we have a 3 by 3 determinant A11, A12, A13, A21, A22, A23, A31, A32, A33, and the two vertical bars. We say the definition is the following. We get the first element, A11, and then remember how we perform. We cover the first row, we cover the first column. You see we have a 2 by 2 determinant. So it's A22, A23, A32, A33. And we name this M11. We name this 2 by 2 determinant M11. And then subtract A12. What is A12? A12 is here. And when we have A12, we do the following thing. We cover the first row and first column. You see you have, again, a 2 by 2 determinant. That's A21, A23, A31, A33. And then we do addition, A13. A13 is here. So A13 is in the first row, third column. So we will cover the first row and the third column. So we get A21, A22, A31, A32. So this is the definition. And here, this 2 by 2 determinant, we name it M12. So those indices are the same as A12, this M12. This is A13, this is M13. So Mij means you remove ith row and jth column. You get that determinant, that is Mij. Right? We had several. Oh yeah, last time I didn't mention this is called the minor. A minor. Okay, there are several minors. This is a minor. This is a minor. This is a minor, and it is a plus, minus, plus. Now let's give a systematic definition about those stuff. So we have definition for an n by n determinant. Let's talk about the general case, not just 3 by 3. For an n by n determinant A, the cofactor of entry Aij. What is Aij? Here, Aij. I means ith row, jth column. Cofactor of Aij denoted by capital Aij is given by what? Aij is equal to -1 to the power of I plus j and times the manner Mij, where Mij is the minor of Aij. It's a minor of Aij. Okay. So cofactor is almost the minor Mij, but you have to multiply it by the coefficient -1 to the power I plus j. So for example, if we have A11, A11 is -1 to the power 1 plus 1 times M11. 1 plus 1 is 2. -1 squared is 1. So A11 is just M11. And A12 is negative 1 to power 1 plus 2 M12. So negative 1 plus 2 is 3. Negative 1 cubed is negative. So it is equal to negative M12. And A13 is negative 1 to power 1 plus 3 M13. 1 plus 3 is 4. Negative 1 to fourth power is 1. So it is equal to M13. Alright, so we just try to use this as example. So you see here, A11 is M11. So I'm going to call this determinant A. So capital A, this 3 by 3 determinant is equal to A11 times M11. M11 is A11. And then this is subtraction A12, M12. I will combine this negative sign with M12. Negative sign combined with M12 is just A12. So it's, if we use the cofactor, we will see this sign becomes positive because its negative sign is combined with M12. And M13 is A13. You see, that is advantage of the cofactor. For cofactor, it's always addition. Cofactor is always called addition. And this, we call it A is expand. A is expand along the first row. A is expanded along the first row. Okay, so how do we get the expansion along first row? The first element in the first row, the first element times the corresponding cofactor plus the second entry times a corresponding cofactor, third entry times a corresponding cofactor. So it's always a multiplication with the corresponding cofactor. It's always addition if we use cofactor. All right. So for example, let's still use this one as example. We can expand it along the first row. We can also expand it along any other row. Let's assume we choose the third row. If we choose the third row, it should be written like A31 times the corresponding cofactor A31 and plus A32 times the corresponding cofactor capital A32 and plus A33 times the corresponding cofactor capital A33. And this is expansion along the third row. Or we can expand expand it along row. We can also expand it along column. For example, let's say we expand it along the second column. The first entry in the second column is A12, and then you have a capital A12 and plus A22 times a capital A22 and plus A32 times a capital A32. This should be also the value of a 3 by 3 determinant. Well, at this moment in this class, we cannot explain why they are all equal. They all give the values of 3 by 3 determinant, but they do give the same evaluation. We will see the example. Okay? So the n by n determinant can always be expanded as a combination of entries and the corresponding cofactors. It's always addition. If we talk about cofactor, it's always addition. If we talk about minors, it's alternating, plus minus plus minus. It's not always first plus and then minus. For example, here, check here. A12 is negative, M12. So actually, if we use minor, it's like this. It's actually minus plus minus. It's not always plus minus plus. It can be minus plus minus, but it's always alternating. The next one is always the opposite of the previous one. So that's why we say we always memorize the cofactor form. Cofactor form, we just use addition, no subtraction. I mean, in the formula, no subtraction, but when you evaluate them, the terms can be positive or negative. Okay, now let's just verify. Let's verify our definition is correct by the examples. This example was discussed in the last video, but still we use this as example. So we have determinant 3, 1, negative 1, 4, 6, and 2, 8, negative 2, 8, negative 2, and 3. So in the last video, the last example, if you go back and check it, the determinant is 122. We calculate by expanding the determinant along the first row. Now let's choose the other one. For example, let's expand it along the second row. I'm not going to copy it. Okay? Expanded along second row is like this. So it's 4 times, what is this position? This is A21. So this is capital A21 plus 6 capital A22 plus 2 A23. Right? This is cofactor. Remember, this is cofactor. Now let's compute cofactor. A21, you cover the first, second row, first column. Can you see it? Oops. Second row, first column. Second row, first column. Yeah, this one is right. Second row, first column, 2, 1, second row. You will have 0, negative 1, negative 2, 3. So A21 is negative 1 to power 2 plus 1, 0, negative 1, negative 2, and 3. 8 is covered. There's no 8. Yeah, this one is better. Right? Second row, first column. And the negative 1 to certain power is always part of the formula of the cofactor. And then you copy this determinant. This is negative sign. Negative 1 cubed is negative. And here, 0 times 3 is 0. Minus negative 1 times negative 2 is positive 2. Negative 1 times negative 2 is positive 2. 0 minus 2 is negative 2. Negative sign is positive 2. And A22 is negative 1 to the power 2 plus 2. And determinant. Second row, second column. Let me see. Yeah, second row, second column. Just so you will see you have 3, 8. 3, 8, negative 1 and 3. Okay, negative 1 to fourth power is positive 1, so you don't see this coefficient. So then you get 3 times 3, 9, minus negative 1 times 8, negative 8. So it's a 17. And A23 is negative 1 to power 2 plus 3. And this is a second row, third column. Second row, third column, right? Yeah, second row. Okay, so you get 3, 0, 8, negative 2. So negative 1 to fifth power is negative. And 3 times negative 2 is negative 6. Minus 0 times 8 is 0. Negative 6 minus 0 is negative 6. Negative 6 is positive 6. See it? So we just get those computation. Now let's go back to the formula. It's a 4 times 2, 8. 6 times 17. 6 times 17. 102. 2 times 6, 12. 8 plus 12 is 20. 20 plus 102 is 122. So you see here, this is exactly this 122. You go back and check the last video. You will see how we expanded the first row and get the 122. Actually, you can try any row or column. Just be careful about the computation of a cofactor. It's always addition. A1 times capital A21 times capital A21 plus A22 times capital A22, A23 times capital A23. It's always addition in the formula, and compute the cofactor carefully. All right, so this is a method to compute whatever dimensions of the determinant. There's an important difference between the matrix and determinant. Matrix is just an ordered array of numbers. The just ordered array of numbers. You can apply row operation. That's a matrix. But determinant is a number. And the determinant is always n by n. Matrix can be n by m, n rows, m columns. N by m matrix. In general, matrix is not always n by n. A matrix can be n by m, especially when you see the augmented matrix. You will always have less row but more columns because you have additional constant column. Okay, so matrix can be n by m, but determinant is always n by n. You will never say, let's say the determinant of 2 by 3. That's impossible for us so far. Okay, the determinant of 2 by 3 is incorrect by definition. Okay, very good. Now let's talk about the Cramer's rule for system of 3 equations with 3 variables. The Cramer's rule to solve a system of 3 equations, linear equation. With 3 variables. Well, again, let's back to the 2 by 2 case. We have ax plus by is s, cx plus dy is t. We have d as a determinant, a, b, c, d. We have a dx. What is dx? You drop the coefficient of x, you replace it by st, constant column, st. You copy the y coefficient, this is dx, the determinant. And dy, you copy the coefficient column for x, you replace the y coefficient by the constant column. Then the Cramer's rule says x is dx over d, and y is dy over d. Well, if d is not equal to 0. The Cramer's rule can be only applied if the determinant, a coefficient determinant is not 0. If the coefficient determinant is 0, there's no Cramer's rule. Okay, so this is a 2 by 2 case. Now let's generalize it to the 3 by 3 case. So 3 by 3 case, we will do this almost identical step. So for example, we have a11 x, a12 y, a13 z. This is we use C1 constant. A21 x, a22 y, a23 z sum is equal to C2. A31 x, a32 y, a33 z, and c. So first d. D is what? D is a coefficient determinant. Let's just put the coefficients. A11, A21, A31, A12, A22, A32, A13, A23, A33. It's a coefficient determinant like this D. And then when we discuss x, dx, we will replace the coefficient column of x by the constant. So we put C1, C2, C3, and other two columns we will keep. A12, A22, A32, A13, A23, A33. You see, the same pattern, we'll just replace x by constant, y by constant, z by constant. And dy, we will replace the y column by the constant. C1, C2, and C3, A13, A23, A33. And this time we will have dz, we'll have 3 variables. We will replace the z column by the constant columns. A11, A21, A31, A12, A22, A32, and C1, C2, C3. You see, you have four determinants. In the 2 by 2 case, you have 3 determinants. Here, 3 by 3, you have 4 determinants. Then the Cramer's rule says, Cramer's rule says that if the coefficient determinant is not 0, then the solution is x is equal to dx over d, the same thing. Y is dy over d, and z is dz over d. That's it. That is Cramer's rule. Very straightforward, very close to the 2 by 2 case. So in formula, the Cramer's rule can be generalized to the n by n determinant case. You have a system of n linear equations with n variables. You will have the similar Cramer's rule. The only thing is that those numbers, when n is very large, those numbers are hard to compute. You see here, 3 by 3 case, even for this one, it's check here, this one, you have to compute the 3 2 by 2 determinant, and then you do the product and add them. This is just for one 3 by 3 determinant. Here you have to compute 4 of them. So it will take time. But anyway, this is our class. We will see the example. Okay. So we have 2x plus y minus z equal to 3. Negative x plus 2y plus 4z is equal to negative 3, and x minus 2y minus 3z is equal to 4. All right. Well, let's try to use the Cramer's rule to solve it. So we're going to compute D. What is D? It's 2, 1, -1. Well, whenever you read the coefficient, you have to include the sign. So it's -1, 2, and 4. 1, -2, and -3. It's a 3 by 3 determinant. Then we're going to compute it. For me, I will always expand it along the first row. It doesn't matter if there's no 0. You always expand it along the first row. It will be 2 times the corresponding minor. 2, 4, -2, -3, minus 1 times -1, 4, 1, -3. See it? You can always find the corresponding minor, because if you expand it along the first row, it's always plus, minus, plus. So that's why I want to do that. I don't want to consider the cofactor. For the cofactor, you have to compute the -1 to a certain power and determine the sign. But if you expand it along the first row, it's always first number times the corresponding minor, and minus second number times the corresponding minor, and plus the third number, -1, times the corresponding minor. So it's a -1, 1, 2, -2. All right. Okay. Let's compute. So it's 2 times -3, -6, minus 4 times -2 is -8. Here's minus -1 times -3 is 3, minus 4 times 1 is 4, and minus -1 times -2 is 2. 2 times 1 is 2. So -2 plus 8 is 2. 2 times 2 is 4. Here's -1. Minus -1 is plus 1. This is 0, so it's equal to 5. The determinant is 5. It's non-zero, so we can apply the Cramer's rule. So we always check the coefficient determinant, see if it is 0 or not. If it is not 0, we will continue. If it is 0, you will stop. Okay, this is D. Then let's check dx. dx, we will replace x column by the constant column. -3, -3, 4. Other two columns, you just copy. Right. And again, we are going to expand it along the first row. So 3. See it? 3, you will see this 2, 4, -2, 2, 4, -2, -3. Minus, here again 1. You have -3, 4, 4, -3, and plus -1 times -3, 2, 4, -2. Just be careful about your computation. This is always a multiplication, subtraction, addition. It's very easy to make a mistake. So it is equal to this 3 times 2 times -3 is -6, minus 4 times -2 is -8. Oops, it's a parenthesis. And minus -3 times -3 is 9, minus 4 times 4 is 16. And minus, this is add a negative sign, so minus. -3 times -2 is 6, 2 times 4 is 8. So this is a positive 2 times 3, 6. What is this? This is -7, minus negative sign is +7. Minus -2 is +2. It's supposed to be 15, right? Yeah, we got 15. So we got dx as 15. Let's continue. We still have 2 more determinants. So dy dy, you'll keep the first column and third column, 2, negative 1, 1. And you copy the constant as the second column. Okay. Then you compute. So 2 times negative 3, 4, 4, negative 3. Minus, this time it becomes 3. 3 times negative 1, 1, 4, negative 3. Just use your pencil to cover the corresponding column, corresponding row. And plus negative 1 times negative 1, negative 3, 1, and 4. Okay, so it's a 2 times negative 3 is 9. 4, 4, 16. Minus 3 times negative 1, negative 3 is 3. Minus 4, 1 is 4. Minus negative 1 times 4, negative 4. Minus negative 3 times 1 is negative 3. So it's what's this? It's negative 7, negative 14. That's negative 1 and plus 3. It's negative 1 and plus 1. So negative 10. It is negative 10. Right. And dz, we keep the first two columns. I'm reading this column and this column. They are from D. We keep the first two columns and replace the third column by the constant. Okay, again I'm going to expand it along the first row. 2, negative 2, negative 3, and 4, minus negative 1, 1, negative 3, 4, and plus 3, negative 1, 1, 2, negative 2. Okay, 3, see, this one, 2, this one, and this one. Okay, well, 2 times 4 is 8. Negative 3 times negative 2 is 6. Minus negative 1 times 4, negative 4. Minus negative 3 times 1, negative 3. And plus 3 times negative 1 times negative 2 is 2. Minus 2 times 1 is 2. This is 2 times 2 is 4. What is this? Negative 4 minus negative 3 is negative 1. Negative 4 plus 3 is negative 1. Minus negative 1 plus 1. This is 0. That's 5. Okay, fortunately we finished them. Then as a result, the solution is x is dx over d. With dx? Dx is 15. D is 10. No, d is a 5. D is a 5. So x is a 3. Y is a dy over d. Dy, where is dy? Dy is negative 10 over 5 is negative 2. And z is dz over z. Dz over d is 1. So the solution is a 3, negative 2, and 1. That's it. So it took us a long time, but eventually we computed correctly. Okay, so that is the solution. So it will take time. In the exam, you're supposed to go through all the steps and get the right answer. You have to do practice. Okay, the Cramer's rule has a hypothesis. Determinant. The matrix coefficient determinant is not equal to the coefficient determinant is not equal to 0. So the discussion or remark. First remark, if the coefficient determinant is equal to 0, but the dx, dy, and dz has non-zero term, at least one non-zero term, at least one non-zero term. For example, maybe dx dy are both 0, but dz is not equal to 0. If this happens, the system is inconsistent and has no solution. Okay, so if it has at least one non-zero term from dx dy dz, then this system has no solution. If they have more than one, of course it has no solution. One will give us inconsistent conclusion. Okay, and second, if d is 0 and the dx dy dz are all equal to 0, then the system has infinitely many solutions. But in this case, the Cramer's rule cannot give you the solution. The system must be solved by row echelon form. You have to go back to the row echelon form, use the matrices steps to solve it. Okay? So the Cramer's rule has a very neat formula, but it has limited application. It can only be applied if you just have a single solution. The matrix method is a universal method. It will tell you single solution, infinitely many solution, or no solution case. Okay, so this is the remark. It's very important what will happen if the coefficient determinant is equal to 0. And now let's discuss certain properties of a determinant. The property 1. The value of a determinant changes the sign if any two rows or two columns are interchanged. If any two rows or two columns are interchanged, then the value of the determinant will be changed to the negative, opposite sign, will be changed to the opposite sign, not negative, opposite sign. So we are not going to give the rigorous proof, but we just see it by we check it by 2 by 2 determinant. Two by two determinant, because it's simple, it has a very straightforward AD minus BC, straightforward formula. We can check it. For example, if we interchange the rows, we will have CDAB. What is the determinant of CDAB? It's a BC minus AD. So this diagonal minus this diagonal. BC minus AD is just negative AD minus BC. Right? It's just negative. So you see here the determinant will change the sign if you interchange the row. What happens if we interchange the column? If we have BD, AC, BD column and AC column, let's check. It's a BC minus AD. is again negative of AD minus BC. So if you interchange two row, just two row, or interchange two columns, you do not change a lot about determinant, but you have to add a negative sign. You have to add a negative sign. Okay? And another thing, if all the entries in any row or any column equals 0, the value of the determinant is 0. So why? You see, remember that we have the expansion A11, A12, A13, A21, A22, A23. And for example, the last row is 0. So what can we do? We can expand it along the last row. 0 times A31 plus 0 times A32. This 0 is A31, little A31. It is equal to 0. This is little A32, little A33. We expanded by the cofactor. So it's 0 times capital A31 plus 0 times capital A32 and plus 0 times capital A33. I don't even care what are the values of a cofactor, but they multiplied by 0, so it's always 0. Okay, so if you observe that one row has all the entries 0, then this determinant is automatically 0. Okay. So that's from the definition of a unbound determinant. Another one, if any two rows or any two columns of a determinant have corresponding entries that are equal, so one row is totally identical to the other row, then the value of the determinant is 0. Why? So for example, you have, there's one thing. If a number is equal to the negative a, then this will imply a must be 0, right? Because you can move this negative to the other side. You will get that 2a is equal to 0, so a is equal to 0. We're going to use this property. If we have row and another row, they are identical. See, the corresponding entries are equal, for x, and this is determinant. We can exchange them. We can exchange those two rows. If we exchange those two rows, we suppose by the first property, we exchange two rows. We're supposed to have a negative a. The values will be negative. But those two rows are identical. You exchange them, you still look. It still look like the first one, so it has to be equal to a. You exchange them, but it is identical to a, so it has to be equal to a. So negative a is equal to a, then it implies a must be 0. That's the property. So two rows are identical, then it is 0. Check this, 1, 2, 1, 2. I don't want to use the 3 by 3 determinant, it's too long. So it's 1 times 2 minus 2 times 1. If you have a 3 by 3 determinant, 4 by 4 determinant, whatever dimension, this property always correct. Two identical rows or two identical columns will imply the determinant is 0. Okay. Okay. Next. Next theorem says if any row or any column of a determinant is multiplied by a non-zero constant k, the value of the determinant is also changed by a factor of k. It's also changed by a factor of k. All right. So what does it mean? It means the following. So for example, A, B, C, D. This is a 2 by 2 determinant. The value, we call it A. And now I'm going to multiply the first row by k, non-zero of course. Then what is the value? The value is going to be k times A. So we just multiply one row or maybe one column by a constant k. Multiply the column 1, so it is k times A. So that's what it means. Okay, you multiply one row or one column by k. Okay, so for example, let's play it. We have 1, 2, 2, 4. Let's multiply the first row by 2. 1 times 2 is 2. 2 times 2 is 4. And because we multiply first row by 2, so it is equal to 2a by this property. But this first row, second row, they are identical. It's supposed to be 0. 2a is 0. A is 0. Right? Well, we can check it. 1 times 4 is 4. 2 times 2 is 4. 4 minus 4 is 0. Of course, that's correct. So I play this example. I just want to tell you all the properties are compatible. You will not say, okay, from this property you get 0, from the other property it's not 0. That means definitely some computation is wrong. Okay? Okay, so next, the final theorem. The final theorem. If the entries of any row or any column of a determinant are multiplied multiplied by a non-zero number. We always multiply something by non-zero number. If it's 0, the result will be 0. It's not interesting. Non-zero number k. We multiply certain entry by non-zero number k. And the result is added to the corresponding entries of another row. If you originally use row, then this is row. If you originally use column, here you use column. The value of the determinant remain unchanged. Well, let's see what does it mean. So for example, we just use 1, 2, here's -3, 4. Remember the row operation. Here you can handle row, you can handle column, but let's just use row operation. I want to make this quantity 0. I want to make this position 0. How do I do it? I multiply row 1 by 3 and add it. You see, you multiply one row is multiplied by a non-zero number. We multiply first row by 3, 6. Don't change it, just multiply first row by 3 and add this correspondingly to the second row. Now let's not make the equal sign. 1, 2, 3 plus -3 is 0. 6 plus 4 is 10. So that's a process. Now let's compare those two determinants. This one is 1 times 10, 10, minus 2 times 0. 2 times 0 is 0, not 2. 2 times 0 is 0. 10 minus 0 is 10. Here, let's check this one. 1 times 4 is 4, minus 2 times -3, -6. 4 minus -6, 4 plus 6 is 10. So you see, unchanged. So that row operation, you multiply certain row by a non-zero number and add it to another row. This process does not change the determinant. You see here, 3 row operations. Row operation. We can multiply a row by a non-zero constant, but it will change. Multiply row by k. It will get ka. K times the determinant. Interchange rows from a to -a. This is not equal. Interchange row from a to -a. 3. Multiply row and then add to another row. A is still A. So in the row operation, 2 operations, in 3 row operations, 2 of them will change the determinant, but 1 will not change the determinant. So those properties just help us to connect the row operation and the determinant. All right? So this section has a lot of formulas and the properties. You see here how many properties we have discussed. 1, this one, interchange, negative sign. opposite sign, and two rows are identical, determinant 0, and 3 any row, no, this one means all rows are 0, the determinant 0, and 3 two rows are identical, determinant 0. 4 times k, determinant times k, and 5 times k added to another row, nothing changes. So we have 5 properties. You have to do some practice and be familiar with them. All the exercises in these sections are important. Do them, ask me question if you have. Okay? Thank you very much. We're finished today. Let me show you all the notes. First page. Page 2. Page 3. Page 4. Page 5. And page 6, final page. Thank you.